Welcome back. The idea today is to learn a few tools and tricks that we usually use when trying to solve integrals that arise in loop calculations in quantum field theory. So the point where we stopped last video is when we got to these two integrals right here coming from these three loops, right? And this one down here that came from the loop appearing in the 2-point function of lambda phi 4. You can notice that these three integrals are pretty similar to each other in structure, right? And this is not a coincidence, right? This is the typical thing you get when you're trying to calculate loops, not only in lambda phi 4, but also in more complicated theories, right? You have an integral over the loop momentum, you have some propagators here in the denominator, right? And so the tricks we are going to look at today will be useful in general, right? Even for more complicated quantum field theories, right? And the two specific things we want to look is the Feynman parametrization and Wick rotation. We'll see that using these two techniques, we can actually solve these integrals and get to the expressions we need for these functions that will allow us to finally find out the value for the counter terms on the renormalization of lambda phi 4, which we have been doing for the last 3-4 videos. And then we'll be able to discuss that a little bit. The first thing to notice is this structure in the denominators here. You always have this product of polynomials in momentum, right? You have this momentum square minus something. In this case, a combination of momentum square minus something, which is typically the thing you have from propagator. So the very first trick you want to look at is how to make these denominators easier to have to integrate, right? So, and that's what we call Feynman parametrization, right? So the idea here is to take a denominator that looks like this. Let's take the first example, right? The simplest one, right? It's just something that is 1 over the product of two terms, right? And write these terms as a single one by using this relation. So I introduce a parameter here, x, right? And the integral in x from 0 to 1 of this denominator, let me write it, x a plus 1 minus x b square, right, goes back to that. That's easy to show. I won't do it here, but you just have to call this guy some variable, do the change of variables and go back. It's pretty easy. And you see you get back to the expression, right? And also you can write a little bit more general one, which is to write in this way, in terms of two parameters now, x and y. Right? But then you put a delta that takes you back there. And now this denominator right here becomes just 1 over x a plus y b squared. Right? This second one is not, usually we use it in this form, but the second one it's more useful if you want to generalize to more terms. These two guys right here, x and y, right, which are integrated, is what we call the Feynman parameters. Right? So you're writing your denominator, this thing that's usually in the integrand of loop integrals, in terms of integrals over these Feynman parameters. So instead of solving integrals, you're introducing more integrals, which is kind of counterintuitive. But what you get from that is that this is easier to integrate in momentum. Right? There's a few other versions of these parametrization equations which are very useful. So you can have one, for instance, if you want, for instance, say like we have here, right? We have here one term times another one, but this second one is to the power of 2, right? It's squared. So in principle, we would need something like 1 over AB squared. This is easy to get. You just have to differentiate this expression right here in relation to B. So if you take dB of 1 over AB, you get that, right? With this minus right here. And on the right side, you can do the same, right? If you apply that either here or here, right? It doesn't matter. I think it's easier to do it in this case right here, right? You get an integral from 0 to 1 dx. Now you have to differentiate this part, which gets you to 1 minus x, and then xa plus 1 minus x b cubed, which I can again write, if I want in a more general way, I can write as this: dx dy, the Dirac delta, x plus y minus 1 over this. So by simple differentiation, I can get bigger powers in this denominator right here. Now, if I do the derivative on this side, of course, I'll get something like 1 over, in fact, 2 over AB cubed, right? If I also include a minus sign in the derivative. And this factor 2 here will cancel this one, right? But when I differentiate this part, I'll get a 3 there. So the 2 will be substituted by a 3, and you increase the power in y, right? So you can write, just by doing that again and again, you can write the general thing, which is a over abn, as an integral in this version right here of n y n minus 1, because you're always exchanging this power to be equal to this one, and the same denominator that increases again and again in power up to n plus 1. So it's easy to get this one just by doing the derivatives, and that's an important one that we will use a lot, so I'll put a box around it. Right? There's also the most general one, which I'll write here, which is something like, suppose you have many of these terms, right? Something like a1, a2, all the way to an. So you have n different terms that you want to parameterize. In this case, the most general expression in terms of also n Feynman parameters, which here I'll call x1, x2, x3, and so on and so forth, all the way to xn, will be something like delta of the sum of all the parameters, in xi minus 1. So they all add up to 1, right? And the integrand looks like n minus 1 factorial x1 a1 plus x2 a2 plus, you get the drill, all the way to xn an to the power of n. Right? So this one is really general one. I won't prove it, but there's a video on YouTube with the full proof of it. It's like 20-minute proof, right? By induction. Essentially, all the information you need is to know this very first one, right? Once you have this one, you can obtain the ones like that by derivatives, by doing derivatives, and you can get this one by induction, right? You just have to prove that the expression for n plus 1 can be written in terms of the expression for n, and you go down all the way to the expression with just two denominators that we have on the top. Right? I'll link the proof for that in the description of the video, because it's already on YouTube. Right? So now I can use those Feynman parametrizations to do the integrals I have right here. Right? And we'll start with this one. I don't know why I could start with any of them. I just picked one at random when I was doing my notes. And this is it, right? So let's start this by applying the parametrization. So what I need to use here is that one with a p square, right? Just call this guy a, this one b, right? And then I can rewrite this denominator. Let me separate just the denominator here. I can write this guy as an integral from 0 to 1 dx. I will use that version with just one Feynman parameter. 2 times 1 minus x over x times this one of these terms. Let's take this one. It's kp squared. Let me fix this. Kp square minus m square plus I epsilon, right? This guy right here. And then 1 minus x, which is y, right? The second Feynman parameter, but I'm keeping just one of them here. K square minus m square plus I epsilon. And this is all to the cube, right? Now I can do some simplification here. You can realize already there are many terms that will be concealed, right? Because I have a minus x here, an x here, so all this will conceal between the terms that are proportional to x, right? So let me just rewrite this guy as, so I just have to do some algebra here, just multiply everything, and you'll see there's a lot of cancellation, and what's left is k squared plus 2k scalar p, right? The part that does not, that is just p squared. Oops, oh, there's x2 here. And then p squared x. The part that involved k squared x concealed against this one, right? And the same for the mass times x and I epsilon times x. So now I'm just left with the part that is 1 times this, which gives me k squared minus m squared plus I epsilon, right? So that's the expression for this denominator. So let me rewrite the expression here. I can bring this guy down here, right? There's a factor 2 here that will eliminate the 2 that is outside. So this is just lambda squared. I want the integral in the Feynman parameter to be up front, because then I will just integrate in momentum now. Let me just make this a little bit bigger. The denominator here changed, right? So I have this times this one. There's a 1 minus x here. And the denominator is this cubed, but I will use this expression right here. So is this thing to the cube, right? So this is what our expression looks like now. Huh? One of the big advantages of the Feynman parameterization, let me move this up top, is that you always get something just like that, right? It's something that the highest power in the momentum in the loop is to the power of 2, and some complicated stuff with it, right? But this complicated stuff can be at most linear in K, right? And that means that I can complete the squares here to make this dependent only on some power of some variable square, right? I can do that by a change of variables. I can invent some L mu, right? Which is K mu plus something. And I can find what this guy needs to be in order to eliminate this cross term between K and P, right? And have something that is a complete square in L. Right? That's pretty easy to do. In this case, I can just take this to the square and compare, and the conclusion will be that K mu needs to be X P mu. So you can make the change of variables, right? Which is defining this L mu is equal to K mu plus X P mu, right? And this is a simple change of variables in this integral, right? dk k4 will go to dl4, right? d4l. And the denominator here, let me call it d, right? Will become just L square plus x 1 minus x p square minus m square plus I epsilon, right? This is just changing this guy. You get an extra term, which is just like this one, which eliminates it, right? And then you can write this, of course. I'll define at this point some variable, and we'll always do something like that, which I'll call L square minus, and this is the new one, delta square plus I epsilon. This is just to simplify my life, because I'll be carrying that delta around, but delta square is just m square minus x1 minus x p square. And then, of course, the numerator here, also under this change of variables. So these happen here, and then I have this numerator, which becomes, just have to do the change right here, right? This will be minus 2L scalar P minus P square plus 2P square X, right? Which I can rewrite as minus 2L scalar P plus 2X minus 1P. This is all just algebra. I hope I'm not missing any signs as I'm copying here, but this is all algebra, right? You just have to take this definition right here and use it everywhere, right? This allowed me to rewrite the whole 2-point function I'm calculating, 4-point function I'm calculating as the integral. Just bring this 1 over 1 minus x outside here and write the integral, which now is in this other 4 vector, which I called L. So d4L over 2 pi to the 4th. The numerator is right here. So it's 2x minus 1 p square minus 2L scalar P. And the denominator got really simple. It's just this guy here. And we have to remember the definition of this delta square that I defined up here. So keep that in mind, right? We'll use it when needed. Eventually we'll have to integrate in X, and then I have to come with back with this. But as far as L, the integration in L is concerned, this is just a constant, right? So that is good. And it's even better if you notice that all the integrals in form momentum L, right, go from minus infinity to plus infinity, right? And this is an even function of all these L0, L1, L2, and L3. And this guy, this term right here in the numerator is an odd function in any of them, L0, L1, 2, or 3. Right? That means that all these integrals are zero. I don't have to care about this guy just by symmetry, since it's the integral of an odd function on a symmetric interval. This is zero. I don't have to worry about this part. So I only have to do the integration for this thing here, and of course with this denominator. Now, seeing this integrand as a power 2 of this 4 vector, and having to integrate in D4L, it's very inviting to try to do this in spherical coordinates, right? The thing is, we're still in Minkowski, and that's not so easy to do in Minkowski. So we want to ideally go to a space where this is an Euclidean 4 vector, because even if I'm still in 4D, I can do spherical integration in spherical coordinates in 4D. And in order to do that, I'll use a trick. We used that already a few videos ago, which is called Wick rotation, which now I'll define more properly, right? We used before just as a change of variables. Now we take a more proper look into this. So the idea is to make an analytical extension to the imaginary plane, right? The complex plane for the integral in L0, right? In order to do that, we have to be careful with the poles of this integrand. In that region, we want to extend our do the analytical extension of our function, right? Have to be careful about poles. So let's look for the poles first. So L squared minus delta squared plus I epsilon can be written as, in the metric we're using, is just L0 squared minus L vector square minus delta square plus I epsilon, which then can be, I can group these two together, right, and rewrite this expression as L0 square minus L square plus delta square to the power half minus I epsilon, everything squared. Right? This epsilon is not really this one, right? That's why you have to be careful. Just take this expression, take to the square, and you go back there and you see you have to rename epsilon, but that's fine, right? And this makes really clear where the poles are, right? You have a pole in this guy minus I epsilon, and another pole in minus this guy plus I epsilon. And that, if you draw on the complex plane for L0, right, will look like this. So now I'm extending L0 to the complex plane, right? The integral I had before is this red one, right, called C1 here. The path of integration is C1, right? And the poles are here and here. Right? Now I can complete the path, right, by putting these two green curves here and the blue one. These two green paths of integration, they will contribute nothing, because if you look at the integrand, right, there's a big suppression here as L0 goes to infinity, right, as happens with these two curves. Once you extend the limits on the red one to minus infinity and plus infinity. So these two will contribute nothing, and that means, since I'm doing a path here that has no poles inside, right? That means that the total integral in the whole path should be zero, and that the sum over path 1, let me put that in red right here, from minus infinity to plus infinity, which is what C1 tells me to do, right? Of any function of L0, dL0 plus, now the integral along the blue curve, C2, that goes from plus I infinity to minus I infinity of the same function, right? This should be 0 due to Cauchy's theorem, right? And that means that the integral, this integral right here, should be e minus this one, right? And then I invert the limits of integration to eliminate that minus. So it goes from minus I infinity to plus I infinity f L0 d L0, right? This relation right here allows me to exchange the integral along the red curve for one along the blue one going up, right? Because I flipped the limits of integration. So I can do now a change in variables, right? You can exchange L0 by IL4, right? Which means that L squared will become minus L4 squared. This was L0, right? Square minus L vector square, which is an Euclidean 4 vector, right? The square of Euclidean 4 vector now, because I could put this minus in front. And that integral right there, these two, can now be written as I integral from minus infinity to plus infinity of the L4 instead of L0, right? F of I L4. So I can do this change of variables and still have the same answer, right? There is one caveat here that is you have to be mindful of, right? The position of these two poles is only really where I have drawn them if this piece right here is positive. That means that either delta square is positive, right? Or more generally, L plus L square plus delta square is positive, right? And that's not always true, right? If you go to the definition of delta, you see this is p squared can be positive or negative because this is Minkowski p, right? It's the external momentum going into the diagram. And it could be in principle negative or in fact positive, right? Negative is okay because then these all will be positive, right? And delta is positive. But if this guy is positive and big, right? Bigger as this x minus, we'll do this analysis more carefully later on, but this thing is limited between 0 and 1/4. So if this guy is bigger than 4m squared, then this can be negative, right? And of course, L is also being integrated. It goes very close to 0, right? The vector L. So this can become negative and complicate things here, right? So what I'm doing here by assuming L squared is bigger than the 0 is limiting myself to the region where p squared is smaller than 4m squared, right? And then I'll have to extend my results to the region where p squared is greater or equal to 4m squared. When I do that, I'll find poles and we'll have to be careful when doing that. But keep in mind, I'm doing the calculation in this region. and I'll have to extend to all regions later, right? So that's the caveat we have to keep in mind. With that in mind, we can go to our expression. Let me find it. This is what we are integrating now. I'll copy it down here and do the Wick rotation. So let me put it here. This is 0, I can eliminate it. And now I have to do a few changes here. So this guy becomes minus LE, right? Which then allows me to take a minus outside. Let me put it here for now. Change the minus here and here, right? This guy becomes ID4LE, right? And this is it. This is essentially the thing we have to integrate. Now, this is independent of L, so really the integral is just d4L of this denominator, which I can do in spherical coordinates. So we know that d4L Euclidean of any function L E that only depends on the module of L, which is the case here, right, is the integral of LE cubed DLE. When I write it just like that, it's just the module of this 4 vector, d omega E f of LE. I can do the integral over the solid angle because nothing depends on the angles here. That's just an extra 2 pi square in 4 dimensions, right, for the solid angle in 4 dimensions, times the integral. And now I want to change, since I have here LE square, I want to exchange the integral in DLE for an integral in DLE square, because then this is more straightforward for what I need. This is easy because LE times DLE is half the LE square, right? So I'll do this change here, and then I have the LE square over 2. I have to compensate here, absorb an LE here, so there's an extra LE square f of LE. Right? Now I just have to exchange this f by the proper thing here and rewrite an integral that I'll use again and again, which is, let me write it in full here. So what I'm saying is that d4LE over 2 pi to the 4th 1 over LE square plus delta square minus I epsilon cubed is equal to 1 over 8 pi square. So I already did a cancellation between this term here and this one, right? And integral from 0 to infinity of d E squared over 2, right, taken from here, times LE squared over this guy. Now, if I do the small changing variables here, right, just to make it more explicit, I can rewrite this. There's a factor 2 goes outside, and I can do these. I'll just call U is equal to LE square over delta square. Right? That means I can rewrite this integral as 1 over 16 pi square. There's a delta that comes out from the change of variables. Integral from 0 to infinity of du times u over 1 plus u minus I epsilon. Again, it's not the same epsilon, it's kind of something like epsilon times or over delta, but again, we are assuming delta is positive, different from 0, so I'm doing all of these in a region where it's safe to do manipulations with this delta. I don't have to worry too much about it. I can never change when I do these redefinitions of epsilon. The important thing is it should be small, real, and positive, right? So I cannot change the sign of epsilon or make it complex. So what I'm doing so far, so I don't have to be too much worried, right? So now this is the definition of a beta function, right? There's this definition of a beta function, which I can write in this way. And then I can also rewrite this beta function as a product of gamma functions. Because in my case, this is very useful because in my case, if you compare this integral with this one, right, all these z's that are here are actually integers. So it's very useful to have gamma functions of integer numbers, right? I just have factorials all around, which are easy to calculate, right? In fact, the plus I epsilon here forces me to do an order change or just take epsilon to 0 and then come back with the epsilon later. In any case, I can rewrite now this integral in a very convenient way, which is that the integral, this one, is just looking here, right? It's just beta. So z1 is 1 here, right? No, z1 is 2, so I have a power 1 up here. Z2 is 1, so I have a cubed here. So this is this is the beta function of 2, 1 over 16 pi square delta square minus I epsilon, right? Because of this I epsilon here. And these I can rewrite as gamma 2, gamma 1 over 16 pi square delta square minus I epsilon gamma 3, using this again. Z1 is 2, Z2 is 1 in my case, right? And since these are all integers, I can just use the factorial of n minus 1 for all these gammas, right? And I have a 2 factorial down here. The rest is just 1. So I have a 32 pi square delta square minus I epsilon, right? Which is a very simple answer, actually, for a very complicated integral. Right? Now I want to go back with these in my 4-point function up here. So now let's copy this guy all the way down here. I put it right here. Right, this I'll bring outside. I lambda square. This is just independent of the L integral. So let me put it here. There's a minus. Let's just organize this in this way. Right? And this thing is the same as here. I can exchange by that. Let me put this one here. right? And do a little bit more of organization. I can write this as minus I lambda square p square over here. All these numerical factors go down here. And the integral over x will now have these two terms, 1 minus x, 2x minus 1, and then this denominator. Remember that delta square is a function of x, which I'll write explicitly now. It's m square minus x, 1 minus x, p square, minus I epsilon. Now, this is quite usually the end of a loop calculation, or at least the analytical part of a loop calculation, because it's not uncommon for it to be impossible to do the analytical integration in the Feynman variables. But realize that even in those cases, you have reduced something that started as a 4 momentum integral to an integral in just one variable in this case, which is much more trackable numerically. In this particular case, you can get an analytical expression for this integral. It's not a pretty one, but you can, right? In fact, when we want to have that analytical expression for all regions in p square, right? And remember that we did that assumption that delta was positive, and now we have to think a little bit about it, right? So delta square is just m square minus x, 1 minus x, p square, right? This is delta square. And you can see here, just by the limits of this integral, that x times 1 minus x is always positive. It goes from 0 in one end, right? This is 0. In the other end is 0 again, right? And in the middle, it has some maximum, which is 1/4, right? You get exactly in the middle, you get the maximum value, which is 1/4. So this guy is bound in that region and always positive. That allows us to see what happens if I demand that delta square is positive, right? These two together mean that you can only keep this positive if p square is smaller than 4m squared. If it's negative, is fine. If it is smaller than 4m squared, this part will never win over m squared, right? So this will always be positive. But once this guy goes above this point, then there's always some value of x, right? Because this can be arbitrarily close to 0, right? That allows this thing to go negative, right? So the moment you go above this point, the moment you go to p squared bigger than 4m squared, then delta squared can be smaller or equal to 0, right? And then you find these subtleties. You have to when you're doing this integral, right? Essentially, because when you are in this region, right? In this one, then you can just remove I epsilon from here, right? Since this guy is always positive, it's never 0, right? I can remove I epsilon, do this integral. The moment I go here, then I have to keep the minus I epsilon and do the integral properly. This is an integral that could easily fill another 30 minutes of video, so I won't do it here, right? But it's just this process, right? The usual process when you have polynomials over polynomials. You have to separate these into these divisions between simpler divisions between polynomials. You have to divide these by these, complete squares, all these tricks that we do to make these just many logarithms, right? You can write these as an integral over 1 over x something, so polynomials, right? I think the first one In fact, the first one for this condition in my lecture notes. You can take a look there for it. And the whole answer is taken from this reference, right? And here it is. Now, about this answer, the specific form is not very enlightening, right? But there are a few things that we can see here, right? The first one is that for the initial diagram we were calculating, right? This one, let me get some color here. For this one, the physical region is really this last one, right? But for the S and T channel, S and U channels, then you can have different combinations of p square, right? P square can be other things, and that's why we are trying to have a most general expression possible, right? Also, that allows us to use these expressions when you have these loops inside more complicated Feynman diagrams. The second thing is to notice that the moment I hit this condition, right, which is physically very meaningful, right? If you think of this diagram, is only, and P is the total momentum going in here, right? It's the sum of these two momenta. It's only when P square is bigger than this number that these guys can be real. They can be on shell, right? Not real, on shell, right? So not virtual particles. And we'll see that's very common feature, and we'll explore that a little bit later, right? Analytically, what is happening here is that once you go above that point, this function, notice that here I have an I, and always an I on this side, right? So gamma tilde is real in this case, and it's also real in this case. I just have to eliminate the I on both sides of this equation, right? But once I go above that point, then it develops really an imaginary part, right? Again, this is related to this possibility now of producing intermediate state of two on-shell particles, right? Keep that in mind. We'll go back to this discussion further on in future videos. This is actually slightly wrong here. Should be a p square here and a p square here, because this is the general expression. Let me see if there's any s anywhere else. No, that's fine. So now what I want to do is apply the same process, right? Feynman parametrization, Wick rotation, and then integrals in this Euclidean space to all of the integrals I had at the start of the lecture. So let me find the next one. Let's go up here and get the next guy, which is this one. So now I want to do this integral, and later I'll be doing that one with the same method. So this is what we are dealing with now. And the first thing to do, right, step one, is Feynman parametrization. So I want to rewrite this denominator here in terms of Feynman parameters. So let me copy everything that just repeats down here. And now I have an integral from 0 to 1 over the Feynman parameter. And I can use that formula for a b squared, right? So this becomes just 2 times 1 minus x from the formula, and the denominator is now x times one of these terms, right? K squared minus lambda squared plus I epsilon plus 1 minus x times the other term, this one, that goes right here. And this all is cubed. Right, let me extend this line. Right, now I call this denominator d, and I have to simplify it and complete squares, right? In this case, d will be just k squared. Just take the time, this term times 1 here is k squared times minus m squared plus I epsilon, right? And then I can do the cancellations between the minus x part and the x part. So k squared goes away, I epsilon goes away. You know, all I'm left with is this part, which is minus x lambda squared, right? And here is plus x m squared, which I can regroup here. So I can group this guy with this guy, right? And write these as x minus 1 m squared. Put up here, put it up there, right? And then always bring the I epsilon to the end just to organize stuff. And this is now this expression. And this guy right here, all this part I call minus delta square, right? Effectively writing k square minus delta square plus I epsilon. And let me save the definition of delta square for later. Right? A box right here. And already this is much simpler than the previous case, right? Because one, I don't have to complete squares. This is already perfect square in k, right? I don't have this cross term with p. This is not even dependent on p because I'm calculating the 4-point function at p square equals 0, right? And also delta square is much more simple now because lambda is some big regularization scale parameter which is much bigger than m squared. So this is always positive. Now things are looking much more simple, right? So let me put that up there and get all the numbers together. Oops. Bring that here. These two goes away with this one. I can change the order here. I bring the integral over x to the front because now I want to do the integral over k later. So this guy goes here, and then I have this integral of 1 over this, which is this rewritten, right? So it's k squared minus delta square plus I epsilon to the cube. Right. So step 1 is Feynman parameterization. That's done, right? Step 2 is Wick rotation, right? So now I didn't have to complete square, so I'm still with k as a variable here. I'll do the rotation in k naught, right? Going to I k4, right? That means k square will be minus k Euclidean square, right? Which allows me to simplify this one. I'll get an extra I here, right? When I change d4k to d4k Euclidean, there's a minus, there's an I that I'll put up front. Right? So minus I lambda square. And I also get this guy to become minus k Euclidean. There's an overall sign here that I'm taking out, so this becomes positive, plus delta here, minus I epsilon, right? And this overall sign goes out and eliminates this sign up front. Right? So now we got the very same integral we did, right? It's exactly the same integral we did over here. Let me find it. This one, right? Just instead of L, I have K there, but everything else is the same. So I can immediately replace that expression by this one down here. Let me copy it again. So this guy multiplies this expression. I copied from up there because I had exactly this integral that I did in terms of beta functions and then gamma functions. So I can simplify all of these as 1i lambda square 32 pi square integral from 0 to 1 dx. And now there's the integral in the Feynman parameters, which in this case is just 1 minus x over, I have to spell out delta, right? In this case, delta is x lambda square minus x minus 1 m square minus I epsilon. Right? This one Mathematica will actually do for you in a finite time. The previous one is harder. It really gets complicated when p square goes bigger than 4m square, and that's not easy to do in Mathematica. But this one is you can straight out put in Mathematica and take the limit of epsilon going to 0 later, and you get the following answer. I actually don't need this label here for this function. It was defined without it. This is just I lambda square, capital lambda square over 32 pi square times a complicated expression. Let me put it here. The log of lambda square over m square minus lambda square which is equal. It's useful to write this by pulling this lambda out because we know that lambda is big compared to m. So it's useful to write this in terms of m over lambdas, right? To see what the limit is, right? And this looks like the following. I just take all these lambdas out and do a cancellation with this one, cancel with this one. This will be 32 pi square times now m square over lambda square minus 1 plus the log of lambda square over m square over, again, m square over lambda square minus 1 square. And then it's easy to take really the limit, right? So m square over lambda square is basically it's 0, right? So I can disregard this part. There's a minus 1 here. This part is just minus 1 square, so it becomes positive. I can rewrite this as, let me copy this part. Will become this log minus 1 from here. Right? And even that, if you go to really big lambda, remember, we had already done the analysis for this part, and we know that is divergent logarithmically, right? This divergence is now appearing here, right? As I take this parameter to infinity to recover my divergence, this is diverging as the log. That means I can also forget this -1 here, it's just doing nothing, right? So this is really it. This is the expression we were looking for. Right, so now we know it's a divergent quantity as we expected, and later we'll do the renormalization conditions. This part needs to cancel with the counter terms, right? Which is the next step. But before that, there's still one integral to do, and here it is. So we follow the same procedure, starting with Feynman parametrization, which again is done by this AB square formula, right? Again, we have that structure, so I can copy this part, right? This also repeats, and I have the integral from 0 to 1 over the Feynman parameter, right, of 2, 1 minus x over x times the first guy here. Let me copy it. Plus 1 minus x times the second guy here. And that's all cubed. Right? Now I could go forward simplifying this thing as before, but I want to use the results we have before, and that's easier if I do a small change in variables. So if you define y equal to 1 minus x, you can rewrite this expression in a more familiar way, almost the same as the ones we did before. It becomes just the integral from 0 to 1 dy of 2y over 1 minus y times this guy plus y times the other one cubed. And that I can, again, same thing, right? I won't redo all the algebra, right? I can just expand here and rewrite this denominator in the useful way, right? Just write it here, bring the integrals in dy up front, and the integral in d for k will be of 1 over k squared minus delta squared plus I epsilon cubed. In this case, delta square is y lambda square minus y minus 1 m square. Right? Again, it's simpler analysis, right? This guy is much simpler. Also, I don't have to complete the squares here. Now I do the Wick rotation. And rewrite this as take the 2 away. When I do the Wick rotation, I have an I coming from here. When this guy becomes Euclidean, there's an I. When this guy becomes Euclidean, there's a minus, which I take outside. So equal to minus I. And again, this integral is that one we know the answer to. So I can rewrite this just as one over 32 pi square delta square minus IF. Right, which then I can just do some organization and rewrite as minus I lambda over 32 pi square lambda, capital lambda 4 integrals from 0 to 1 dy over times y over y lambda square minus y minus 1. Here I'm just writing delta square explicitly. M square minus IF, right? Which is the expression we want. Ideally, you have to do the integral in y. That's another one that Mathematica will do for you. Just copy this down here. And you get minus I lambda over 32 pi square lambda 4, and then the integral will be just lambda square minus m square plus m square log of m square over lambda square over m square minus lambda square square. And again, I can do that thing, I just take all the lambdas out and take the limit, which will give me this guy is equal to lambda square minus m square log of lambda square over m square, right? Which, as predicted, right, when we analyzed this loop, we got the conclusion that it diverges quadratically in the parameter. Here it is. There's also a logarithmic divergence, right, which is there. So now that we pay the price and suffer through all these integrals, we can indulge ourselves a little bit in some physics fun, right? And see what happens with the counter terms now that we have analytical expressions for them. So let's start with the renormalization condition for the coupling constant, right? We have seen that it implies that this counter term needs to be equal to the loop part of gamma 2 calculated at some reference point that so far I have called as 0, t0, u0. And we also know that this 4-point loop function is given by this expression, which we have been calculating, right? Gamma L. But this guy is given by gamma L of S plus gamma L of t plus I gamma L of u, right? And also we managed to separate within each of these gammas the finite part from the divergent part, right? So all the divergent integrals are contained here in gamma L calculated at p equals 0, and you have this other function, gamma tilde, which is finite, right? So that's all we got so far, and we calculated this guy and this guy. Now, to go further, I need to specify this reference point, right? So I need to choose values for S0, T0, and U0, right? Of course, now I'll just choose points which are convenient for my calculation, right? Not necessarily points that are easy to experimentally measure. In fact, I would choose this one where S is 4m squared, t is 0 and u is 0, which makes everything very easy, right? But of course, that's not easy. This is almost like, this is like a scattering where the two initial particles are at rest, right? And this is not really a scattering. It's not very practical to measure a scattering like that. But since we're doing a theoretical calculation here, this is the easier point to use, and none of the conclusions really depend on this value, right? So going up here, I can rewrite delta lambda as, right, this expression here, right, which is gamma L of 4m squared plus gamma L of 0 and gamma L of 0 again, so 2 gamma L of 0, right? And of course, this guy here, right, I can use this expression. For this other two, it's not needed, right? Because if I put 0 on both sides of the equation, I see that gamma tilde of 0 needs to be 0. But this guy I can rewrite as gamma L of 0 plus gamma tilde L calculated at 4m squared. And that means I can rewrite this guy as gamma L tilde 4m squared plus 3 gamma L 0, right? And now I can use the expressions I have for these guys, right? So gamma L tilde of 4m squared, right? I can get from here, right? Remember we had this solution, and for 4m squared, the equation is really this last one. Let me copy it here. And I just have to exchange p squared for 4m squared, right? So when I do that, when I put p squared equal to 4m squared, this becomes 0. Also here becomes 0, becomes 0. So this whole middle part goes away because there's 0 in front and the logarithm is not diverging. In fact, it's becoming the logarithm of 1, which is 0 too, right? So let me get rid of this guy, and this becomes just 2 plus I pi, which is pretty neat. And also gamma L of 0 is something I already calculated. Is just, also I don't have this I here because before I was calculating I and you had I here and here, right? So now I'm removing the I on both sides of this equation. Same here, I put the result I had before without the I. It's just lambda square over 32 pi square log of lambda square over m square. And now I can put these two things together and rewrite delta lambda. Let's just have to add those two together. Delta lambda will be lambda square, 32 pi square. I remember there's 3 contributions from this guy, so it's 3 times this log plus 2 plus I pi, right? So now I know the counter term, delta lambda. But that also means I can know the matrix element for these 2 to 2 scattering that I was calculating from the start, right? At the very start, I wrote that the scattering matrix element is up to order 3 in order 2 in lambda, right? It's just minus lambda minus the counter term plus gamma 2 of S T U. This is where I define these contributions to the loop. This is where I define the counter term, right? This comes straight from the renormalized Lagrangian, right? Plus contributions of order lambda cubed. Now, if I do substitute these expressions I have up here in here, I'll get that this guy, which now clearly depends on S, T, and U, right, will be given by minus lambda. Now this part is just, let me write it like that. This is minus gamma tilde L of 4m squared plus 3 gamma of 0, right? I'm using it as I wrote it up here. Plus this guy, right? Which I can write as gamma tilde L of S plus gamma tilde L of T plus gamma tilde L of U, right? Plus 3 times gamma 0. Gamma of 0, right? Gamma L of 0. Plus higher order corrections, right? So what I did here is just write each of these 3 contributions here, this one, this one, this one, in this way. So I got 3 times gamma of 0 and the 3 gamma tildes calculated of S, T, and U. Now, the conditions imply, right, were made so that this guy cancels out this one, which is the divergent part. So everything that's left is finite, right? I have expressions for these guys, and they are all finite. So what I'm obtaining is that this guy is minus lambda plus something that is the sum of these 3 minus this, which is all finite, right? Plus higher order corrections. So here is something we have basically predicted before, right? That once you put one loop corrections in this theory, the matrix element itself will become dependent on momenta, right? There are 4 momenta going into this diagram. I combine them into these 3 variables, S, T, and U, but you can see that this is influencing the value of the matrix. And this dependence on S, T, and U is in relation to that reference point. Remember, I choose a point which was 4m squared, 0 and 0 in this STU space, right? And it's clear here that if I put 4m squared here, 0 and 0, again I get that m of 4m squared, 0, 0 is just minus lambda, as I wanted. But now, no matter where I could have made other choices, so this value of minus lambda would be defined somewhere else. But once I know the value at one point, I can move away from that point, and this function right here will predict to me what the matrix element will be in different points, which I can then go and measure again and check. So I'm making here a prediction which is testable through experiments, right? Needless to say, this kind of prediction, especially for QED, but also for QCD, have been tested to very high degree of success, and that's why people actually believe quantum field theory to be a good theory, right? So this is a definite prediction, which was buried under a divergence, right? If I was just to look at these divergences and say, well, this is non-physical, I would have missed this, right? But in fact, what you can see is that differences, and in this case, what I'm talking about is the difference between m at this point, this reference point, and m at some other point. This difference is not divergent, right? While both of them can be divergent, the difference is not. And so if you focus on that, you see physical effects, right? So that's the important message as far as the coupling constant to go. Now the renormalization of the 2-point function is much more simple in this case, right? I had written that the 1pi, this is the sum of all the 1pi contributions, is given by the counter term. Let me write it like this, right? Plus this one loop contribution we just calculated. And this I could rewrite as this way. This is just the counter term, p squared delta z minus delta m squared. So this is the counter term for the field renormalization constant and for the mass renormalization. And this is the loop we just calculated. I'll write it here explicitly. 32 pi squared times these divergences, right? It's the square divergence and the logarithmic 1. And these two counter terms could be obtained by the demand of the position of the pole and the residue of the pole, which translated in these two conditions, right, which we have seen before. So delta z is equal to the derivative in p squared of the loop contributions to m squared, right, of p squared, calculated at the point where p squared is equal to m squared. So these loop contributions are exactly these ones, right? This is minus I m squared loop. This is this term right here. Right? But you can see here that this does not depend on momentum. This does not depend on p. So in effect, delta z is 0 for this theory at this order in perturbation theory. Right? This is very simple, right? And it's not general at all, right? This is just a fluke of lambda phi 4 at one loop. It just so happens that this loop does not depend on p squared. If you go to higher orders or to more complicated theories, this won't be true, right? And in fact, that's why we didn't do the Taylor expansion for this guy, right? Like we did for gamma. For gamma, we did the Taylor expansion to separate the finite part from the divergent part, right? And in here, the Taylor expansion would be trivial. It would be just the first term, right? And that's just a fact at this order in perturbation. Now, if you do the second consequence, right, you had also renormalization condition for the mass, right, which looked like this. So p squared delta z minus delta m squared should be equal to m loop square of p squared, right? And this is true only at p squared equals m squared, right? This comes from demanding this guy is the pole. And this one comes from the value of the residue. Right? But now, since delta z is 0, this is 0, right? And you get that delta m squared minus this contribution, which is written up here, right? I have to remove the I, right? And this is minus im squared, so this contribution will be just this part, right? So this is just lambda over 32 pi square, lambda square minus m square log of lambda square over m square. And there's a minus here because this is minus m loop square. In this case, there's not much to say, right? This is clearly concealing the other contribution coming from the loops here, and defines the physical mass, right, as measured, right? You could measure it anywhere because this does not depend on p squared. So I could really have set this condition at any other point because this is too simple at this order, right? So that's all I wanted to say for this video. Thank you for the audience.